Good. Okay. First of all, thank you, Rework. It's great to be back in a conference in person after 2 years. Feels great. So I'm going to be talking about representation learning on graphs and its applications and innovations across the pharma value chain. So I work for a central data science unit within Novartis, and we work across the spectrum. So I'll be showing a lot of graph use cases from various parts of the business. How does this move? Okay. Before we start, just want to acknowledge the guys who really do the work. So this is my team: Abhijit, Megha, Preeti, Pamoli, and Smita. I basically just attend meetings. These guys do the real work. So hats off to these guys. Actually, whatever I present is being done by these guys. To start off with, just a philosophical slide of sorts. What I wanted to say is, as far as I understand it, at least. We can call deep learning or machine learning of anything as basically a triumvirate, the Caesar, Pompey, Crassus, triumvirate of geometry, linear algebra, and optimization, right? So anything we're trying to do in machine learning or deep learning, we're basically saying that, these are points in high dimensional space, and we want to separate them or regress towards them or extrapolate them or something of that sort, right? And the way to do it, because it forms a very complex landscape, is we have to navigate it, right? And just like, if you have a vehicle which is traversing through this complex landscape, you need to find that minimal point, the valley out there, right? And our vehicle in this case is linear algebra, right? Of course, calculus thrown into the mix somewhere over there. But these are the triumvirate that kind of makes machine learning work or deep learning work. The problem is this, that somebody like me, well, this is a problem because I'm essentially really bad at maths. And when I have to do something like this, I'm like, oh, problem. And for people like me, thankfully, there's this mathematical trick called graphs. So what I do is I try to put everything into graphs so that I don't have to navigate these things, all right? And for people who ask me, why do you put everything into graphs? I just say, hey, the real voyage of discovery is not about trying new things, but just having new eyes to see it. So I look at everything as graphs. But the problem is, so deep learning in the last 10 years or so has really made a difference, right? Really made a difference in terms of how we can navigate various different prediction problems. But when it comes to graph structured data, our deep learning algorithms as we know it, our LSTM or a convolution neural network, are they effective in handling graph structured data, especially in the embeddings framework, right? Deep learning generally captures a lot of hidden patterns in Euclidean data. But when it comes to graph structured data, not everything holds true. So how do we navigate that? Now, if you look at graph neural networks, so graph neural networks was devised as a part to handle graph structured data. And there are a lot of graph structured data, right? Now, if we break up graphs or graph neural networks into three main classes, at least that's what I do. A conv GNN, a convolutional graph neural network, which basically runs a convolution, but not on the grid, but across a graph. And it basically encapsulates each layer's hidden representation by aggregating certain features. Right? It aggregates the features, except it's not on a grid, it's across the graph. Then we have auto-encoders, just like we have normal auto-encoders, we have graph auto-encoders. Again, it's a representation learning framework. The encoder is basically nothing but layers of graph convolution, which is embedding each node, and the decoder is then decoding whatever has been embedded by the first layers of the convolution networks, right? Now, we apply nonlinear activations, of course, and the decoder basically reconstructs the adjacency matrix from that. And the third one, which is a little bit more complicated, is when we have the additional dimension of time in there. Now, graphs, as we know it, are often difficult to represent time or time elements in it. But when we have time elements in it or a sequence in it, that's when problems happen with the traditional conv GNN or the variational autoencoder kind of models, right? So that's when we look for something like, so there are rec GNNs as well, the recurrent graph neural networks, but STGNNs kind of capture it anyways. So we have typical time elements to it, and we have the typical graph in 3D space. What we do is we use kind of a graph convolution network, but also with 1D convolutions, which kind of takes care of the time element of it. You can also replace the con-GNN, sorry, not the con-GNN, but the 1D CNN with reg GNNs, and that should work equally well, right? And finally, we take a multi-layer perceptron, which kind of aggregates all of this together and throws the output back. There are various variations of this, but kind of all of them, all graph neural networks fall into one of these classes. And I'm going to talk about examples where we've used all of these kind of to solve real-life business problems and certain problems that we face with it, right? Now, the first problem that we were tackling was in our manufacturing division at Novartis. Now, at Novartis, we are a very large pharma company, right? And we buy stuff worth almost $17 billion. And when you buy that much amount of stuff, and typically what happens is, because we don't go like, hey, you know, we have labs, and there's a huge amount of procurement that goes into the labs, but it's slightly different from a typical e-commerce or retail, in the sense we don't go, hey, this is a good-looking beaker, let's just buy it, right? We want to buy the same beaker across different vendors, but which one is better in terms of quality, which one is cheaper, etc. So what we were trying to do is use knowledge graphs and graph neural networks to understand and streamline procurement patterns in our manufacturing units and in our research divisions, right? So we have various kinds of data. We have products, orders, suppliers, clickstream data from people using it. And what essentially, before we built this, we called it the buying engine, by the way. Essentially, what used to happen is, a guy in the lab would call up his favorite vendor and say, hey, get me these pipettes or beakers or something like that. There was no, interface where you could go look, check, and then buy. It was pretty much a manual process. And what we wanted to do was build like an Amazon or a Shopify or a Flipkart for internally within Novartis, right? What we did is we did a semantic integration of various data sources. These kind of data sources, products, orders, users, and suppliers. And what we try to do is try to recommend hey, this is the best possible chemical that you want to buy from various different vendors. Right? So that was the problem statement, and because they're very complex data sources, so this was a slightly older one, but we have around 3.5, so this is for one particular category. We had 3.5 million products from different vendors. We have various properties that each of these items have. And another problem that we had was, initially at least, when the catalogs come, it is in the manufacturing divisions, it's not like an Amazon catalog or it's not like an iPhone catalog, right? That's here's a camera, how many megapixels it is, here's your Super AMOLED display, a screen, or whatever. It comes pretty much as a basic text. It's a paragraph of text. That's how it comes. So what we did was we built an NER first. A custom NER, which we broke the properties up, down in each of these free text catalogs, and then projected it as a graph. And then we put it on an interface, and people could interact with it. Our scientists and our manufacturers could interact with it, right? So we built this graph, which is a product, property, and user graph. Of course, there are sessions in it, so there is clickstream data in it. And then we embedded it. And what we're trying to get is things like this, that what is the user to product property edge weight? So which user prefers which products, right? And are there similar users which we can recommend the same thing then? User to manufacturer weights, that are there certain users who prefer certain manufacturers, right? Every scientists particularly have their preferences. They're like, hey, I have always used VWR chemicals, this is Thermo Fisher chemicals, and I always found great results with VWR. I'm not going to move anywhere. So are these kind of preferences that are there, right? We wanted to understand that. And vendor weights also, right? Okay, that who calls whom? Somebody used to call somebody else, but we can understand from the buying patterns again, that who prefers what kind of vendors. So that was the premise. Now, again, like I said, it's not all about recommendation in our thing, because we're not trying to, increase our sales. We're trying to actually decrease our sales or make it cheaper. So that's why we wanted to understand these user properties, so that we understand what kind of change management needs to be done. Also, to convince users that, hey, you know what, you don't need to buy the most expensive beaker out there. Here's a beaker from a local supplier which is equally good. but cheaper. So our objective was to save money. And what we did was a variational autoencoder on one side, and the spatio-temporal, it was a spatio-temporal graph, because we have user sessions in there as well, so preferences change depending on what you're manufacturing at that particular moment. But it was basically, it was a 1D CNN on the time axis, but it was basically a variational autoencoder. Typical variational autoencoder, the architecture is what I showed. It is basically 3 layers of graph convolutions. Each convolution has multiple layers again within it. We encode it, and then there's a decoder which is recreating the adjacency matrix. And what we find is ultimately insights such as this. The users who clustered together, there are certain users who clustered together, there are certain users who are very completely idiosyncratic, they do whatever they want. We also get, these patterns that which product and properties do certain users prefer, what do they want to buy, and we can use that to recommend other users that, hey, what, your colleagues are buying this and they're finding equally good results probably. And use that for change management purposes as well, that we go talk to them and say, guys, this is what your preference is, somebody else is using this, they have equally good results, maybe you should consider doing this. And all these insights was basically obtained using graph neural networks, right? We constructed a graph database. We used a combination, it was done at scale, so right now there are almost 3 billion products in it. It's scaled across 26 different countries. We have manufacturing sites in various countries around the world. So it's been scaled to 26 different countries, and that's what we are. And it's showing savings. It's showing almost 15 to 20% savings, right? Basis of it was, again, the graph neural network. I'll dive more into the graph neural networks a little bit on what kind of strategy we are using also in subsequent slides. Now, again, to go with another quote, that in my perception, the world wasn't a graph or a formula or equation, it's just a story, right? So using a similar kind of concept or similar kind of graph architectures and graph neural networks, you can actually create stories about various different things. And that's what I'm going to show. The next thing that I'm going to show, and again, this is something that we've been working on, is how we interact with our customers. Now, in the pharma industry, our customers are the doctors, and then we have consumers, which are the patients, right? And how can we use graph neural networks again to understand peer-to-peer influence networks? Now, doctors talk to each other. Doctors talk to each other. They're influenced by each other. And what we wanted to understand was influence patterns, right? So that we know, and also interests and stuff like that of each individual doctor, so that when we communicate with our customers through our marketing communications, our sales communications, we wanted to understand what should we talk to them about, and who should we approach, who's the main doctor out there that we should talk to him, and then things get automatically passed down. So this is a typical graph network that comes up. This is, for example, in the US, where we tried to understand, using graph neural networks, key opinion leaders, digital opinion leaders, understand about, get a 360 about each individual doctor. And what we did was, again, we constructed a knowledge graph, pretty much a hand-constructed knowledge graph, which included various different data sources, various dimensional data sources. We had trials, how many trials did they participate in, how many publications they're involved in, what kind of interactions have we had with them, so our internal data as well, to understand that. Primary market research, we do primary market research quite a bit, so the primary market research data was included into that. Real world evidence, so this is claims data from insurance companies that pharma companies can buy, and it basically shows paradigms or treatment paradigms that various doctors follow. Some people, for rare diseases, some people want to go steroids first, and some doctors go biologics first, right? So there are various treatment paradigms. We wanted to understand that, so that our communication can be tailored according to their preferences and according to their likes and dislikes, right? The whole idea was to move away from a brand-based marketing, which we in pharma have always done, to much more modern marketing, which is driven by what people's interests are. So customers are not just interested in a brand, they are interested in experience. So experience-based marketing is what we wanted to go to. Now, when we talk about multimodal data of this sort, right? So like I said, there are two types. So one is we have a social network. A social network of doctors, obviously, which is constructed based on, okay, these guys publish together, or these guys participate in trials together, right? And they are part of the same provider network and the same hospital, or they have attended school together, etc., right? So you have a social network, and then there are events. The events are either real-world evidence events that when a patient came to them, how did their prescription pattern look like, or when we approached them with our communication messages, how did they interact with it? So these are events, which is you're given in your eye, right? Now we tried two different strategies. The first one was we had two separate GNN blocks, one which was looking at the user event interaction patterns separately, and the second one, and the social network itself separately. So there are two different GNNs. The embedding matrices of this were combined together and concatenated together, and from there two MLPs were used to ultimately get the results out, right? The second strategy we used was take those individual graphs that are there and then combine them together into one single graph. This is an engineering problem because the graph tends to get really, really big and really, really complex. It also becomes a multi-graph because sometimes, doctors can share the same social network in multiple ways. So there can be multiple edges, right? So it becomes a multi-graph. So it's an engineering problem, first of all. And the way we tackled that engineering problem was simply we combined two different graph databases. We used an OLTP as a store where the entire transactional data was going in. And we used an OLAP combined with the OLTP that was also a graph database. Two different types of graph databases were combined together, and we created a very, very scalable graph database system, which could actually house something like a multi-graph of really, really large sizes. And once we had that full graph, so our GNN blocks was used on top of that. Now, in this particular case, again, we used a graph variational autoencoders with certain modifications. So the modifications are such that I'll come to it again, because there's a hierarchy also in there that, this guy is a KOL and he's a key opinion leader and everybody else follows kind of the same pattern that one particular doctor follows, right? So, but the GNN blocks were combined using, so these two different strategies were tried out for various different use cases within this. Either of them worked. Some of them, when we have to really look at really, really large graphs for certain insights, that's when we shift back to the first one because it's a little bit more scalable system. While the second one can be really, really powerful if we can tackle the engineering problem, as I said, right? So two different strategies that we use with various degrees of success. But primarily we use a second strategy where we combine two different graphs, a user event graph and a social graph together into a single graph, and then embed, get the representation learning on top of that, right? All right. Now, the problem is, again, like I said, sometimes in graphs especially, there are hierarchies. So the graph to success is not always straight, right? It has curves and intersections, and how do we tackle that? And when we talk about graphs, the primary problem that we have is hierarchies. Now I'm going to take a third example when we are looking at clinical trial data, right? Now clinical trial data, as mandated by the FDA, needs to be presented in something called the SDTM format, or the study data tabulation model, which breaks it up into domains, cardiovascular, respiratory, stuff like that, and then domain level study data, and then the relationship data sets, right? So it's a very, very hierarchical pattern that the FDA wants us to follow, which is the SDTM format of data, right? Now, while I'm showing this as an example, this hierarchical form of graphs is prevalent everywhere, right? It's prevalent in the social graph that I was showing for the commercial use case as well. Now, the idea is, when I have a hierarchical graph like this, and I'm trying to use typical graph neural networks or typical embeddings of any form, right? Is it able to handle it? Now, typical embedding frameworks generally do not, because what we use is when we're doing a BERT or any kind of embedding or convolution like embedding on top of it, what we do is we discard a particular vector norm to make the aggregation better, right? Which is problematic. Now, hierarchy, though, is super important because that's how intelligent systems comprehend causality. Many systems include comprehending causality, understanding common sense and logic are hierarchically driven. For example, if you have a mammal, and we can have various different types of mammals, and one is closer to the other than the next. Now, typically, when we have a hierarchical system like this, typical neural networks do not explicitly model this hierarchical relationship because we, again, discard a vector norm, which is useful for representing these relationships. Now, then how do we do it? One way to do it is using, instead of discarding Euclidean embeddings and going into hyperbolic embeddings, right, in a hyperbolic space. The problem with moving into hyperbolic space is this, that our typical matrix that we use, RMSEs and cross entropies and stuff like that, they don't hold true in hyperbolic space. So again, we have to completely construct a completely different framework, which in an industrial organization is difficult, right? You can't convince anybody that your thing makes sense. So what do we do? So what we used is something, we used polar embeddings. So we didn't use a hyperbolic space, but we used the polar space, polar coordinate system. So instead of using Euclidean system, we went into the polar coordinate system. And again, I'm showing it for the trials, but we use the same thing for various different use cases, including the commercial one. Now, polar embeddings have two different variables, right? We have the radius or the modulus of the polar embedding and the space, and the phase or the vector angle, right, as separate parameters. So there are two parameters. It's not just one point in space. What this does is the radius or modulus represents generality, right? While the angle or the phase represents similarity, right? So if I have a device and you have support and a source, and then you have shelf and bookend, right? So these are two different, so you can get the hierarchy embedded in it. So it will, based on your phase and your modulus, you can model both similarity and the hierarchy, right? So that's what we have been trying to use. So we form a triplet, which is your HRT denotes in our knowledge graphs. The corresponding boldface letters, the HRT over there, that is in H, that is in bold, they represents the embeddings or the vectors of the head entities, the tail entities, and the relationship entities. And we use a hierarchy-aware knowledge graph. So what it basically means is that given a radius and a modulus and the HRT relationship, we can model the tail and from the head given a relationship, but it's embedded both in polar space. So we have a radius and a phase, right? So that's what we do. And if basically there exists a relationship between HRT, then a positive sample is basically going to be closer together, while if there's no relationship between them, they're going to be further away from each other. That's how we model most of these hierarchical relationships. This actually, while again it's an engineering problem because you're increasing the number of parameters, of course, which makes it difficult to scale, but you can tackle these engineering problems using good MLOps and good scalable systems. The performance of this kind of a polar embeddings, especially on these kind of graphs where hierarchical relationships are automatically embedded, tends to be much better than simple Euclidean embeddings, which discards the hierarchical relationship, right? So be it a KOL to an individual doctor, or from a domain like cardiovascular to particular parameters within the clinical trial space, this kind of embeddings represents a significant improvement over typical Euclidean embeddings that we get from a conv network or an autoencoder. So we still use the conv and the autoencoder and all of it, except we get two variables out of it, the radius and the phase. So we embed it as in polar coordinates, right? With that, once we have that, then we can model many things as a link prediction problem, right? So we used unsupervised graph sage-like algorithms as our conv networks or our embedding models. These unsupervised techniques, of course, especially in the clinical trial space, helps us a lot because we don't really know what is what. So we used unsupervised embeddings using graph sage. And it represents the structure and the features of the nodes, including the hierarchy, right, by using the polar embeddings. Moreover, the advantage that we have by using a graph sage-like algorithm is that it generalizes better, that we don't need to, especially when you're looking at trials, because we are constantly doing trials on disease areas that we have not seen before. Rare diseases, we just started a Parkinson's trial after 20 years. We started a psychiatry trial, which we've never done before. So there are domains and data that have never been seen before. And unsupervised embedding of this sort does give us an advantage when it comes to completely unseen data, right? We don't need to retrain the embeddings every time. A lot of it generalizes. Good. Finally, just leave with one last quote that I was very happy to realize that I'm not the only one who feels that I'm super bad in maths and need to use graphs. But Charlie Munger, one of the pioneers of this field, basically said that mankind is intrinsically so lousy at manipulating numbers that we invented this trick called graphs. With that, I'm going to finish my talk and happy to take any questions.